Hello, good people. This is section 8.1 of Calculus Early Transcendentals, and we are talking about arc length, and this is an application of integration. So as with setting up integrals, we are using that limit definition of the integral, and here we're going to be setting up an integral that will calculate the length of a curve in the plane from x equal to a to x equal to b. And as usual, what do we do with that curve, or what do we do with the interval of a to b? We divide it into n equal partitions of delta x partitions, and then we begin to approximate the length of the curve by calculating the distance between 2 points, and those 2 points on that delta x interval being the endpoints from a to a plus delta x, and then in the next delta x1, what is the distance between the point P1 and P2, and we use our Pythagorean distance formula, that is the square root of x2 minus x1 plus y2 minus y1, or we can use that delta notation of delta x squared plus delta y squared square root. And that is the distance between those 2 points. And then, of course, we would form a Riemann sum of those distances to add up all of the distance as the whole is equal to the sum of its parts. And then we would take the limit as the number of partitions goes to infinity, and that would form our integral. So we further take some algebraic manipulations of the square root of delta x squared plus delta y squared so that we can get to an actual integral that we set up. And so here in this line, we start with that delta x squared plus delta y squared, and we factor out the delta x squared, and we end up with delta x squared times 1 plus delta y over delta x squared. And then we throw in a little bit of the mean value theorem, because we're dealing with a continuous function whose curve we are trying to calculate the length of, and we're assuming it is differentiable on all of those subintervals. And so by the mean value theorem, there is a point C that is going to equal the average rate of change, and that is that delta y over delta x is that average rate of change. But we know that there, for every single one of those delta x intervals, we've got a point C equal to xi star, where that average rate of change actually equals the instant rate of change, or the derivative. And so we can replace, with our limit definition, we can replace the delta y over delta x with the derivative f prime of x. And so here we have it, the arc length formula. If f prime is continuous on AB, that means it's differentiable, then the length of the curve y equal to f of x from a to b is going to be the integral of the square root of f prime of x squared dx. So let's do a pretty simple example, and then I will set up another example, and you can see that once we set up our integral, we will go back to techniques of integration to calculate the arc length. And then I will go over some strategies for being able to calculate that integral easily. And I remind students that simplification is key, always thinking 2 steps ahead. Once I form the expression for square root of 1 plus dy dx squared and put it into the integral, I actually have to integrate. So you kind of want to set yourself up for an easy integral to calculate. All right, so usually I go through and advise my students to start building or engineer that arc length expression. So we've got, in this first example, y equal to 2x plus 1 on the interval from 0 to 5. And I just say, okay, well, what is dy dx? dy dx is going to equal 2. And then I'm going to square it. What is dy dx squared? That is going to equal 2 squared, which is 4. And then I'm going to add 1 to the dy dx. And I end up with 5. And then I'm going to take the square root of 1 plus dy dx squared, and that's going to equal square root of 5. And I'll take the time now to say, usually when we are building the slice, we'll say that the slice for arc length, that small delta x slice, is actually has a name called the ds, and it comes from the arc length of a circle that is the arc that's trapped by a central angle. They use that as an s, so I believe that the ds here is where they come up with that letter s, and we call that the 1 plus dy dx squared dx. And keep in mind that we can integrate with respect to y, and just keep in mind then that it would be a function d, the derivative of x, with respect to y, and then we would have dy dy instead of dx dx, but keep in mind that those are going to be the same. So our ds here is going to be equal to the square root of 5 dx, and now our arc length is going to be the integral of the ds from 0 to 5, because that's our range of values, and that's going to be from 0 to 5 of the square root of 5 dx, and we know that the integral of square root of 5 is square root of 5 times x, and we're going to go from 0 to 5, and our f of 5 minus f of 0 is going to be 5 root 5 minus 0 times root 5, and that's just going to be 5 root 5. Okay. In the second example, I'm just going to go, and in the interest of time, I'm just going to set it up and then mention how it could be calculated. All right, so again, let's just follow the procedure for building the ds, or building the arc length slice. And so here we do have f of x, and we can use that f prime of x notation if you would like. So my f prime of x is 2x, and then I'm going to square it. And 2x squared becomes 2x times 2x, which is 4x squared. And then I want to add 1. So that's going to be 4x squared plus 1. And then I'm going to take the square root. And that's going to be the square root of 4x squared plus 1. And there's nothing I can do to simplify that. It does not equal 2x plus 1. Do not distribute the half exponent. And our ds here is just going to be the square root of 4x squared plus 1 times dx. And so we now form our integral, and we use our range of x values to form that. So our arc length here is going to be the integral from 0 to 2 of our ds, and that's going to be the integral from 0 to 2 of 4x squared plus 1 dx. So there are tables of integrals out there, so you could, with our techniques of integration, we could use an integral table, or an integral table entry to solve, or you can use a trig substitution, and that trig substitution being let 2x equal tangent theta, right? And you can move forward with that. All right, so at this point, I would like to mention some good substitution or some good simplification techniques to prepare yourself for calculating the arc length. So you want to simplify the square root of 1 plus dy dx squared dx as much as possible before integrating. Because that way you'll have greater success in doing that. And so how would you? So I usually tell my students, if you'll want to make use of exponent rules. And how would you make use of exponent rules? We know that square root of a times b does equal the square root of a times the square root of b. We also want to make use of a square root of a over b does equal the square root of a over the square root of b. So when given, or when building the square root of 1 plus dy dx squared if 1 plus dy dx squared at this moment is equal to 1 plus a fraction, or 1 plus a rational expression. Or even a radical expression, because sometimes you've got some functions like square root of x that would give you a radical expression. But if you've got a fraction there with a numerator and a denominator, then you would want to combine, or to have one fraction. In other words, you'd want to take your 1 and have the same denominator over as the fraction denominator, and then combine the numerators, so do your fraction addition, right? Add the two terms to be one fraction, right? By making a special version of 1 and combining that, and then use the square root of a over b equal to the square root of a over the square root of b. That can often be pretty helpful. If you see after adding 1 to your dy dx squared that you end up with an expression that you can factor something out, you would want to do that. So 2, if 1 plus dy dx squared, which has two terms, has a common factor, consider factoring it out. Consider using the square root of a times b equal to the square root of a times the square root of b. So I would say, like, as an example, suppose the 1 plus dy dx squared is equal to x squared plus x to the 4th. You know that the next step is going to be, let's take the square root, and then we take the square root. But I see in that term, or in those two terms, that I've got a common factor of x squared, because what's going to be my next step? My next step is going to be put that thing into an integral. And how am I going to integrate that? And so I want to set myself up for an easy integral. So I would say that this is equal to x squared times 1 plus x squared, right? Just factoring it out, and then using my radical properties, that's x squared times, or square root of x squared times the square root of 1 plus x squared, and that's going to be x times 1 plus x squared. And if I throw that into an integral, right, if I have that integral there, this would be an integral, and then this would be an integral, and now it's just a u substitution, which is very simple to do. So you kind of want to try to simplify that way. And then finally, the last one that I would recommend is, if you end up with a polynomial expression that can be factored into a perfect square, know that when you take the square root of a perfect square, it just equals the base of that square. So number 3, if 1 plus dy dx is a polynomial, try to factor to a perfect square if you can. Or, like I said, try to factor out some common factor. You could also consider completing the square on that polynomial, and if you complete the square, and this is assuming that the 1 plus dy dx is actually a degree 2, but you could complete the square and consider a trig substitution after that. So, or a table entry. Try to make it a perfect square. All right, so hopefully that gives you some guidance on how to set up your integral so that you can actually complete the calculation. And let's do this one down here to see what I'm talking about. All right, so find the arc length of this function, and where y is goes from 1 to 5. So in this case, we are going to be taking the derivative of x with respect to y, so our ds is going to have a dy differential. Okay, so we start with our x. So we have our x here is 2/3 times y squared minus 1 to the 3/2. And what is our dx dy? That's going to be the chain rule. So let's not forget our chain rule. And we're going to have, that's going to be 3/2, and 3/2 minus 1 is to the 1/2. And we're going to evaluate at the inside, but then we're going to multiply by the derivative of the inside. And now I'm going to clean things up. I know that my 3's cancel, my 2's cancel, and I can put my 2y in the front. And I see here that dx dy is going to equal 2y times the square root of y squared minus 1. And my next step is to square it. And squaring that, 2y times 2y is 4y squared. And the square root of y squared minus 1 squared is just going to be y squared minus 1. And then my next step is going to be, let's add 1 to my dx dy. And that's going to be 1 plus 4y squared times y squared minus 1. And I know that my next step is going to be to take the square root, so I'm going to start simplifying that underneath. So if I do take the square root here, that looks like something that I don't really want to integrate, or it might be difficult to find in a table entry. So I'm going to start expanding that, right? So my ds here is going to be the square root of, and underneath I'm just going to start expanding. So 4y squared times y squared is 4y to the 4th, and then I end up with minus 4y squared. And then I still have my dy on the other side since I've formed my ds. I'm going to continue with my simplification, and in that simplification I'm going to rearrange my ds just to have descending powers. And I have a 4y to the 4th minus a 4y squared plus 1 dy, and I can see that that is going to be 2y squared minus 1 times 2y squared minus 1 dy, right? First outers, inners last. And I end up with, then, since that's a perfect square, then my ds here is just going to be 2y squared minus 1 dy. So here's an example of me looking at a polynomial and seeing if I can change it to a perfect square, which is nice. So what my L then is going to be the integral, and what's our range of values? Our range of values here is from 1 to 5, and so I'm going to have from 1 to 5 of my ds, and that's going to be 2y squared minus 1 times dy, and we can easily integrate that as 2y cubed over 3, take away y, and we go from 1 to 5, and what is our values there? We end up with y cubed times evaluated at 5 is 125. 125 times 2 is 250. So we have 250 over 3, and then we subtract 5, and then we want to take away 1, or the 2 evaluated at 1. That's our f of 5 minus f of 1, and we end up with minus 2/3, take away 1, and simplifying that, we end up with 248 over 3, and minus 5 plus 1 is going to be minus 4, and then you can simplify that to 1 fraction. All right. Hopefully that does it for arc length. I wish you the best of success in this area, and I will see you in the next video.